Hello everyone, my name is Jiajing Chen, a PhD student from Syracuse University, advised by Professor Senem Velipasalar. Today, I'm going to bring the topic of our WACD paper, like in 3D guided way, 3D guided 2D visual image classification. To introduce our proposed method, I want to make a brief comparison of the traditional visual image classification pattern and our proposed one. In the traditional visual image classification, the support images are randomly picked from the database, and the support images may essentially look very different from the current image due to the different capturing angle. In these cases, even for humans, it's very hard to successfully match them. However, different from the traditional one, our proposed method uses the projections from the 3D mesh as the support images. You could see here, the projections cover the complete information of an object, and we could make sure that there should always have one support image similar to the query image if they are belonging to the same class. With the motivation, I want to introduce the angle variety as well as the shape variety here. The angle variety refers to having images of the same object from different viewing angles in the support set. You could see here, for all these 14 projections, they are obtained from the same airplane, but from different viewing angles. However, for the shape variety, that means all the projections are obtained from the same view. You could see here, all the projections are taken from the top view, but from different objects, different identity. Here, we performed the experiment to study the effect of angle variation and the shape variation. In the first experiment, we studied the angle variety for a fixed shape. A 3D object is picked first, then projections belonging to this object are used as support images. In the second experiment, we studied shape variety for a fixed angle. In this time, an angle is picked first, then AK projections taken from that angle, but for different samples from the same class are used as support set. Finally, we studied the mixed variety. K projections are randomly picked from the projection pool, resulting in images representing different view angles as well as different shapes. The experiment results are shown here. You can see, if we only consider angle variety or shape variety, the accuracy converges when the short number increases to 9 or 12. However, if we could consider both variety, the accuracy keeps improving as the short number increases. In the traditional 2D visual learning, because the support images are randomly picked from the datasets, we cannot guarantee the angle variety or the shape variety. However, in our proposed 3D guided 2D visual learning pattern, if we only have one shot, at least the angle variety could be guaranteed because the projections are generated from different view angles. If we have more shots, the shape variety could be also guaranteed. In this section, we performed the experiment to study the view angle contribution to the final performance. Instead of using all 14 projections generated from a mesh sample, in each experiment, we only use projections belonging to either horizontal, bottom, or top view during the training and testing. And this here, we show the experiment results performed on the ModelNet 40 and the ShapeNet with the IOU value. It could be observed that for each class, the accuracy varies considerably depending on whether the support images come from the bottom, horizontal, or top view, and the standard deviation of the IOU value becomes as high as 12.18% and 9.33% for ModelNet 40 and ShapeNet. The reason is that we cannot make sure the query image taking angle is always consistent with the support image taking angle. If these two angles differs a lot, the performance will drop a lot. In contrast, if these two angles are very similar to each other, the support image angle and the query image angle are very similar to each other, the accuracy may be very great. Before the training of the network, we adopted the contrastive learning method to pre-train the backbone here. The pre-training is only performed on support projections images from the training classes. you could see here, we have the support projections generated from 3 different angles. We'll firstly randomly pick up 2 images, I1 and I2, from these 3 images. And then we'll apply the data transformation to the I1, like the rotation, like the background color changing. We'll get the I1 prime. Then we feed the I1 prime as well as the I2 to the shared backbone to get the F1 and the F2. Finally, we maximize the agreement of the F1 and F2 to make the backbone robust to the different background color and image rotation. Here, we show how we train our network. PC is the probability of classifying the project as class C, and PA is the probability of classifying the object angle as A. So let's start with from the most beginning. We have the support projections and the query images. We feed them into the backbone, and we'll have the support projection features and the query features. And then we get the class prototype by averaging all the features belonging to the same class. And then we get the angle prototype by averaging feature belonging to the same angle. For example, if we want to get the PRH of the airplane, we just need to average the H1 to the H5 of the airplane. Then we could get the PRH of the airplane. And next, we're going to optimize the PC and the PAC. Let's talk about the PC firstly. If we want to, we did it the same way as the ProtoNet did. We have the class prototype, we have the query features. For example, if these query features belong to the bottom, we just need to minimize the bottom's query features and its corresponding support prototype features here. That's this value. We just need to minimize it. We will have the classification loss. Next, we're going to optimize the PAC. That is the given the class, the probability of the angle is A. However, because we don't have any information of the angle during the training, according to the Bayesian rules, we have this formula. Instead of optimize the PA in condition of C directly, we could optimize the PA in condition of the C. We could optimize the PC in condition of the A instead, because the PA in condition of C is positive correlation to the PC in condition of the A. So how should we do that? We have the angle prototype here, and we have the query features here. We calculate the distance matrix firstly, and then we sort each row's value, and we get the sorted distance matrix D prime. And for the second row is the bottom, right? Because the query is the bottom, and the second row is corresponding to the distance of the query, the bottom's query and the bottom support features. So we should minimize each value in each column to get the angle inference loss. The final loss is just the weighted summation of the LA and the LC. In the testing phase, we first obtain the PC and then calculate the PA in condition of the C. Once we have these two values, we could get the angle distribution by this marginal distribution formula. Once we have the angle distribution, we could update our prototype by this formula. That is the expected value, expectation of the angle prototype here. Once we have the updated prototype, class prototype, we could use it to better estimate the class of the query image. We first performed experiments on the ModelNet 40 with 1 3D shot and 3 3D shot. The ModelNet 40 dataset contains a lot of 3D objects from 40 classes. We performed 4-fold cross-validation, and we could see here our proposed method greatly outperforms other benchmarks' performance in each fold experiment. The same thing happens for the experiment on the Toys4K and ShapeNet. We also performed the k-fold cross-validation here, and our proposed AINet greatly outperforms other benchmarks' performance. In the previous experiment, all query images are rendered from Toys4K datasets. Here, we use the real-world images collected from the internet as the query set, and we could see here our method greatly outperforms the ProtoNet for each class. Thanks for watching.